So we're now going to turn to the relationship between the heat generated in a circuit element and the current flowing in it, described mathematically by Joule's law. So we're going to kind of take this all into the electrical domain a little bit. A conductor, when carrying an electric current, will radiate heat. This is because that as the electrons flow through the conductor, they'll collide with other electrons and with the molecules of the conductor material. These collisions result in the production of heat. So we've got this, these electrons electromagnetically coming into contact with other molecules and charge carriers, and this friction between these collisions produces heat. We can calculate the amount of this heat produced by a current carrying wire by using Joule's law, named again after James Joule, for electric heating. The amount of heat produced by Joule's law is H, the heat, is equal to the work done by the system divided by the mechanical equivalent of heat. It's not a quiff, a quiv. So that's Joule's law. Let me go ahead and write that out. The heat produced is work divided by the mechanical equivalent of heat. So the mechanical equivalent of heat in joules, a joule is 4,186 joules per kilocalorie. Now, the reason we use kilocalories is because calories are a very common unit used for the measurement of heat. So, using Joule's law to calculate the amount of heat produced by a current of I amps through a resistance of R ohms for T seconds is going to be given by heat equals power times time over that mechanical equivalency, J equals I times V times T. So I can calculate the amount of heat produced by calculating the work done, which is power times time, right? Work, as we discussed earlier, is power times time. Power in an electrical circuit, as we discussed earlier, is I times V. So work is just I, work in an electrical circuit is I times V times T. And then I just divide that by J, where J in this case indicates the conversion of joules to kilocalories. We can make a further simplification of this from Ohm's law, if you recall from previous classes, Ohm's law. And I hope you're all even ahead of me on this one. V equals, let's say it together, IR, right? Say it together. Ohm's law. So we can make a substitution, right? And now we get heat equals I squared R times T over J. Or the square of the current times the resistance times time, right? Divided by, again, that mechanical equivalent of heat, J. Note that this equation is, the mechanical equivalent of heat is simply used to convert between joules and kilocalories, which are still both a measurement of energy. So let's finish up today's lecture by doing an example of Joule's law of electric heating. Let's assume the heating element of an electric tea kettle has a constant resistance of 100 ohms and is supplied by a 240 volt DC source. The kettle contains 1 liter of water and can raise the temperature of the water from 15 degrees Celsius to 90 degrees Celsius in 10 minutes and 52 seconds. We want to determine the efficiency of the tea kettle. Lots of fun. So first, what we need to know is how much heat energy it takes to change the temperature by a given amount. So we've got this liquid water, and we need to know how much heat energy it takes to change the temperature, a unit of temperature. Typically, this measurement is called the specific heat of material. It's given the formula C sub P, and it's measured in joules per kilogram Kelvin. Kelvin being a unit of temperature, right? Joules per kilogram Kelvin. And again, this is specific heat. Right. For water, the specific heat is 4,190 joules per kilogram Kelvin. So you'll notice I wrote this approximately equals sign here. The specific heat of water is actually temperature and pressure dependent, so it's an approximately equal. We're just going to assume it's constant to make our calculations a little bit easier. So now we're going to use this information to calculate the amount of heat taken by the water and the amount of heat taken by the kettle. So heat can be calculated as mass times specific heat times the change in temperature, and this is T final minus T initial. A lot of times we'll see this written as a triangle and then the letter T, that it would be read delta T, meaning a change in T, right? That symbol, that delta symbol, the Greek letter delta, typically refers to a change in. You probably remember that from calculus courses. So mass we can change to volume times density, and so we can write this as volume times density times specific heat times the change in temperature. So H, amount of heat taken up, is going to be volume times density times specific heat times the change in temperature. So for water, this is going to be H. This tea kettle had 1 liter, right? 1 liter of water. We now multiply by the density of water. This one's nice. It's 1 kilogram per liter. You can look at this. Look. Density of water up at standard atmospheric pressure, 1 kilogram per liter. Now we need to multiply that by the specific heat of water, which again was 4,190 joules per kilogram Kelvin. 4,190 joules per kilogram Kelvin. And then we need to multiply by the temperature change, which we started at 15 degrees Celsius and we went to 90 degrees Celsius. So that's 90 minus 15. And you may be screaming at me right now. You might be saying, oh my goodness, you just use Celsius units over here on the delta T, and but you gave us the specific heat in Kelvin. Well, fortunately for all of us, 1 Celsius is equal to 1 degree Kelvin. So if we're multiplying them, we don't actually have to do any conversion. 1 change degree Celsius is the same as a degree Kelvin. The scales just start at different places. So what that means is that in heat energy here, we get 314,250 joules. 314,250 joules. So that's the total heat energy for the temperature change that we've gone through. From Joule's law, we can calculate the total heat produced via the current. And we don't even have to convert to kilocalories. So from Joule's law, we can say heat equals I squared, the current, squared times the resistance, right, times T. We know that this is a 250 volt appliance at 100 ohms, so we can figure out what I is just by dividing 250 volts by 100. So we're going to make that V over R squared. So that's just V over R is just current, and we multiply by R times T. So that gives us another power formula. It's V squared over R is another formula for power in a DC resistive circuit. But so what we end up with is a 250 squared over 100 times the time, 250 volts squared over 100 ohms. And the time in this case was 652 seconds. So we multiply that out and we get 407,500 joules. So now we've got the total heat produced by the current, and we've got the heat that actually went into the water. So what we can do is if we divide 314,000, I guess I should label those. If I divide 314,250 joules, which is the heat that actually went into the water, and by 407,500, I get, well, we'll just do it, 314,250 joules, which was the heat energy that went into the water. We divide that by 407,500. Which is the heat energy that went into the power, right? The resistive load, 77%. So this tea kettle is 77% efficient. Where's the rest of the, in converting electrical heat into hot water? Where'd the rest of the energy go? It made the tea kettle warm, right? If you touch the sides of the tea kettle, you're going to feel a warm metal. So we had to heat up the rest of the tea kettle, right? And the wire that connect to your wall outlet to the tea kettle, that actually has a temperature increase. And the cable that surrounds the wire, it's going to absorb some of the heat. So what has happened is that there's heat energy that is lost in other parts. It's not all transmitted directly into this water. So that's the end of Module 1, Energy, Force, and Power, and the end of this video.